We study elementary second-order differential equations. This is the equation of motion for a particle moving in one dimension under a conservative force whose potential energy is given by U of x. The differential equations originate from Newton's law, second law of motion. This is a differential equation. Equation of motion is the origin of the differential equation. Okay, we solve the differential equation. Very simple one. Second order derivative is itself. We make use of our previous result. The derivative of an exponential function is identical to the original function. We replace this one, y equals e to the x, then y's x derivative is y. So this is also true when if I multiply any constant c to this function, we can multiply c and again c exponential x is a c exponential x. So we have a freedom to choose the normalization factor. If we make use of this, we can take the double derivative, and double derivative is a derivative twice, differentiation twice, and after taking the first order derivative, we have exponential function, and then take the derivative, again the same function. So we can notice that e to the x is a solution for the differential equation, second order differential equation, like this. So is it everything? So is there any other solution? Yes, there is. Let's see. Equals exponential e to the ax instead of e to the x. Its derivative is we can make use of chain rule. So we first take the derivative with this full variable, and this variable is taken by the x derivative. Then this is the same as the original function, and this result is a. So result is ay. We repeat the calculation twice. So d squared y, d squared x equals d dx, dy dx. This is a e to the x, ax, dx, and a dx, d e to the ax, that we obtain a squared e to the ax. Therefore, I know now that y equals e to the ax is the solution for this. By the way, we have a squared instead of 1. What about we compare this equation with the original equation? These are the same when a squared equals 1. That a squared equals 1 has two solutions. A equals plus minus 1. That means I have e to the ax and y equals e to the minus x. Both of them satisfy the equation. Okay, so dx squared d squared e to the x equals e to the x, dx squared d squared e to the minus x, that is again minus x. Multiply c1 multiplied by c2 and add them. Because they are constant, what we have is a second order derivative of c1 e to the x plus c2 e to the minus x equals c1 e to the x plus c2 e to the minus x. So what we find is the solution is a linear combination of these two solutions. Okay? We say these two solutions, e to the x and e to the minus x, are linearly independent. Why? c1 e to the x and c2 e to the minus x is identical to 0 for whatever x you may substitute. It is exactly 0. Independent only if c1, c2 equals 0. If you don't substitute 0 for both parameters, it is non-zero. That is the linearly independent functions. We find, for example, e to the x is increasing and decreasing, and they meet together at x equals 0. So at some point, you can make these two numbers appropriately to cancel these two values. But it is impossible for you to cancel these values everywhere. It is impossible. Therefore, these are linearly independent. What about y equals x and y equals 2x? I can always multiply, for example, 1/2 minus 1/2, multiply, and add them up. So x plus 2x, x multiplied by, and 2x multiplied by minus 1/2. So it is x minus x equals 0. So they cancel. So in that case, this function and this function, they are linearly dependent. So if you have two linearly independent solutions for this second order differential equation, then their linear combination is the solution. Okay? The general solution of a differential equation is a linear combination of basis functions. We call these two are the basis functions. How can you determine whether two functions are linearly independent or dependent? Two functions f of x and are linearly independent if it is exactly 0 everywhere, only if and only if you substitute both constants to be 0. If it's not the case, they are linearly dependent. How many free parameters are required to express the general solution of differential equation? We have constant of integration for each integral. So derivative, if I want to make this derivative to be expressed as y, you need to integrate. If you integrate over x, you will find this value is free. You have arbitrary constant value that can be added in the primitive function. Therefore, for each integral, you have a constant of integration. If you have a double derivative, you need to integrate twice. Then you will find another integration constant. So number of derivatives, the maximum number of derivatives is the order of the differential equation, and equation of motion is a second order differential equation. We have the maximum derivative to be 2. So there are 2 integration constant. And the number of constant of integration represent the number of independent functions that are called the basis functions. So in the second order differential equation, if you find two linearly independent functions that are the solution, then the linear combination is the solution for that. And actually, this is homogeneous equation. Homogeneous equation, that means y is nth order derivative, n minus 1th order derivative, and y and their linear combination. In physics problem, mostly the coefficients are constant, but they can be a function of x. So in that case, this is nth order differential equation equals 0. This is a homogeneous equation. The solution of the nth order homogeneous linear differential equation has n basis functions. If you are able to find n basis function, their linear combination is the general solution, and there is no other solution that cannot be expressed in terms of this. And this kind of space, this is a functional space, but it is very similar to the Euclidean space in which we have n linearly independent basis vectors and whose components express an arbitrary vector uniquely. And these coefficients are something like Cartesian coordinates of a vector. So this is a solution space. The set of all solutions is just like a vector space, and this is a unit base, just like a unit basis vector, and these are something like the Cartesian components of a Euclidean space. But it is not a Euclidean space, but we call it the Hilbert space.